Hello, welcome back to Algebra. The title of this lesson is called Multiplying Binomials with Radicals and Rationalizing the Denominator Part 1. This is Part 1 of several lessons. We'll increase the problem complexity as we always do from the easier problems to the more difficult problems. So what do we mean here by multiplying binomials that have radicals? So in the last few lessons, we've done lots of problems with simplifying radical expressions, learning how to add radicals and so on. And now we're just continuing building our skills with different ways to work with radicals. So if you remember, a binomial is a parentheses with two terms inside. Binomial means two, so two terms inside the parentheses. When you multiply that by another binomial, what we say we're doing is multiplying two binomials together. Now we've multiplied binomials over and over and over again in this class, and the only thing we're doing here is we're involving radicals in there. So we're learning how to mix two things together using FOIL to multiply binomials, but also having to deal with radicals along the way. So if you want to recall, we've multiplied binomials so many times, but I still want to make sure everybody's on the same page. So recall that we have a couple of quick rules that we use that we can use as, I don't want to call them shortcuts, it's just sometimes it's nice to use these things, and we'll use them sometimes in these problems as well. So for instance, if you have a plus b, and you would like to square that binomial, this is a binomial and you're squaring, don't forget what this actually means. This means a plus b times a minus b, right? I'm sorry, a plus b times a plus b. So it's the same exact thing multiplied by itself. So if you don't remember what this equals, or the shortcut way, you can always write it out in the long form way, right? So how do we do it? What we have is we have the first terms multiplied together, so that's a squared. Then we'll have the inside terms, which will be ba or ab, however you want to think about it. Then we'll have the outside terms, which is another a times b. So we add those together, and it'll be 2 times a times b. And then the last terms multiplied will be b squared. So a lot of times what we will say is if we ever are given a plus b quantity squared, we can kind of skip all of this and skip the FOIL and just go straight to the answer. It's the first guy squared plus 2 times the first thing times the second thing plus the last guy squared, right? So that's what we have if we have a binomial like that squared with a plus sign in the middle. Now also recall when we were multiplying binomials, we learned how to handle it if we have a minus b squared. And as you might guess, these are very, very, very similar, so the answers are going to be similar. So this would be a minus b times a minus b. If you forget the kind of the shortcut answer, or the pre-derived answer, then just write it out as itself multiplied by itself. But what we're going to get is something similar here. We have the a times the a is the a squared. But on the inside, we'll have negative b times a, which is negative ab. Then the outside terms will have another negative ab. We add those together, we'll have a negative 2 times ab, right? The last terms is a negative times the negative, giving you positive b squared. So you see how these are almost exactly the same. The minus sign on the inside means you take the first guy, square it, minus 2 times a times b here, and then plus, this changes into a plus, b squared. The reason it changes into a plus is because of the multiplication going on right there. So if you see this, you can skip all of this if you can remember it and just go straight into the answer. If you don't remember that, just write it all out. And then the last one I'm going to remind you of before we start solving problems is if, one thing we learned a long time ago is if we have a squared minus b squared. A squared minus b squared, which is the difference of two squares. That's exactly what this is, the difference of two squares. So you should know by now that we factored this so many times, this is always written as a plus b times a minus b, right? So if you see this, you can always write it as a plus b, a minus b as a broken out multiplication like that. And to prove this to you, to remind you of this, how is this the case? Let's multiply this stuff out again. A times a is a squared. A times b is ab. This is a negative b, so negative b times a is negative ab. And then the last one is negative b times positive b, which means negative b times b, which is negative b squared. And you see what's going to happen here is these interior terms, ab minus ab, is going to go away to 0. So you're going to have a squared minus b squared, which is exactly what we said. So I'm just putting these on the board to remind you, because it might have been, you know, a few weeks or however long ago that you've seen these. Because we're going to use all of these, but we're going to be mixing in having to deal with radicals along the way. So if you have a plus b squared, you can use this. If you have a minus b squared, you can use this. if you have a squared minus b squared as a difference of two squares, you can write it like this. If you forget any of those, it's okay. Don't stress out about it. If you forget those shortcuts, it's okay. Just write it out and multiply it out, which is what I'm going to do most of the time anyway, just because I like to show everything and don't take too many shortcuts. All right. Now, one thing I want to talk to you about in the beginning here, try to make it all the way to the end of this lesson with me, because we need to talk very seriously about something called rationalizing the denominator. We don't want radicals in the denominators of fractions. We've talked about that before. But in this lesson, we're going to have more complicated expressions that will have some kind of radical in the denominator, and we need to talk about how to get rid of them. So in order to do that, we're going to talk about what we call rationalizing that denominator, which means we're going to introduce the concept of a conjugate. And it's a lot of big words, guys, but really all it means is we need to figure out a way to get rid of all the radicals in the bottom. And that's what we're going to do. So make it kind of go through the problems with me, and I will show you exactly how we do that. Now let's crawl before we can walk, right? Let's start small. Our first problem is going to be 3 plus the square root of 7 times 3 minus the square root of 7, right? Now, we're going to multiply it out, of course, you know, but you might also tell yourself, hey, this guy has the form that looks kind of like this. It's a plus b, a minus b, this plus this minus this. So if you were clever, or if you just wanted to skip a step, you could kind of take this and go straight into writing it like this. But I generally don't like to skip steps too much because I like to make sure everybody's on the same page. So let's go multiply it out. First term's multiplied, 3 times 3 is going to give me 9. The inside terms, 3 times the square root of 7 is going to be literally written as 3 times the square root of 7. The outside terms will have another 3 times this negative square root of 7. So it'll be negative 3 times the square root of 7. 3 times the square root of 7 with a negative out in front. And then the last term, you have a negative times a positive, so you're going to have a negative. But what you're multiplying is square root of 7 times the square root of 7. I'm going to write it like this. Square root of 7 quantities squared. One of the biggest things I think students do with radicals when you're squaring things and simplifying things is you try to do too many things too fast. You try to skip steps because you don't want to write anything down. It happens a lot. So you know that square root of 7 times square root of 7 here, that what's going to end up happening is the square is going to cancel with the square root, and you're just going to get a 7 at the end. But resist that temptation just to write that down until you get really, really comfortable. I want you to write it down explicitly so you can remember what you're doing. Now, I want you to notice something very special happened here. We multiplied these two things together. Notice what happened. The inside term here, 3 times the square root of 7, is exactly balanced by this one, which has a negative sign. So when we add these together, we actually got 0 in the middle. So what we actually got at the end of the day, switch colors over here, is we have a 9 here, and then we have a minus sign here, and then as we said before, the square is going to cancel with the square root, so we're going to have this minus, but we're basically going to have a 7 left over. And as you all know, that 9 minus 7 is 2. So 2 is the final answer to this problem. So a couple things I want to point out, and they're all really, really important, so I want you to pay attention, because as we go on through this class, or through this lesson, and also through the few subsequent lessons, we'll be using some of the terminology here a lot. Notice that we had something here with a number and a radical, and we multiplied it by almost an exact copy of itself. The only difference is we changed the sign. This was a plus, we changed it to a minus. Everything else was the same. When we did that, notice that the answer we got has no radicals anymore. If I change this back to a plus sign, I multiply all this stuff out, I'm going to get radicals. The only reason that we have no radicals in the answer is because of this beautiful cancellation in the middle. It's because of the unbalanced signs here. This gave us a positive 3 times the square root of 7. This gives us a negative 3 times the square root of 7. The only way it happened is because we changed this sign to the opposite sign. That's what caused it to happen. So I'm not going to get too crazy about it right now because I'm going to introduce it as we go along here. But this guy here, this 3 minus the square root of 7, is what we call the conjugate. Conjugate. Conjugate, like that. It's the conjugate of something. It's the conjugate of its kind of like its sister term, which is the guy in front of here. It's the conjugate of 3 plus the square root of 7. These are kind of mirror images. You can say that this is the conjugate of this term. Why is it the conjugate? The conjugate just means it's exactly the same term, but you just change the sign in between them. So here this was a plus, we changed to a minus, we say it's the conjugate of this. It just means, the word conjugate you can think of as, it means it's almost like the sister or the brother or the cousin of this term. It's almost the same, it's just got one little change. And likewise, I'm not going to write it on the board, but we can also say that this term here is the conjugate of its sister term here, because if we change this negative to a positive, we get this one. So really, they're conjugates of each other. One is the conjugate of this one's the conjugate of that one. The only difference between them is we change the signs between the two terms that have the radicals in there. Now, important thing for you to know is when we do that, changing of signs, then we have this beautiful cancellation in the middle, and that will happen every time you multiply a conjugate times its sister term. You will always eliminate all square roots. And that is how we're going to clear the radicals from denominators of expressions that have radicals. We're going to be multiplying by the conjugate, because I'll prove it to you as we get into a future problem in this lesson. But every time you multiply by a conjugate, you will kill all square roots every single time. It doesn't matter what the square root is or anything else. If you multiply by the conjugate, you get rid of the square roots. So kind of roll that around in the back of your mind, and let's do the next problem. And just kind of keep this in the back of your mind, because we're going to revisit this idea of a conjugate in future problems. The next one is square root of 7 plus the number 1 squared. We want to multiply this out. Now, of course, you could go up here and you could say, well, it matches this form. I could do this squared plus 2 times this plus this squared. Of course, you could do that. But generally, here in the beginning, I like to write it all out, because some people may not remember those rules. I put them on the board to help us, but still some people might not. So I'm going to do it both ways. So we're going to do it as if we've forgotten that rule, and we're going to write it all out. So it's this times itself, an exact copy. Notice here in the previous problem, we multiplied it by an exact copy, but with only one change. We changed the sign of what's joining these things. And that eliminated all the radicals and gave us just a number. Here, we're multiplying by an exact copy of itself, but this is not multiplying by a conjugate. A conjugate means you have to change that sign. Here we didn't do that, so as you might guess, we're going to have radicals in the answer. So let's go and just double check that that's what happens. The first terms multiplied together is square root of 7 times square root of 7. I want you to write that as the square root of 7 quantity squared. The inside terms is 1 times the square root of 7, which I'm just going to write it as the square root of 7. The outside terms is another 1 times the square root of 7, so I'm going to write that as the square root of 7. And the last terms is 1 times 1. I'm just going to write that as 1. Now here, the square and the square root cancel, so you get a nice number of 7 here. Here you have a square root of 7 plus the square root of 7. You get, let me see if I can write it correctly, 2 times the square root of 7, because we have 2 of them. And then we have the plus the number 1. So we can add the numbers together, which gives us 8 plus 2 times the square root of 7. 8 plus 2 times the square root of 7. You try to simplify that, but 7 is a prime number, so even if you do a factor tree, you can't simplify it. You certainly cannot add these together. So it's really important for you to notice what happened here. In this problem, we multiplied by an identical copy of itself, and we still had radicals in the answer. We can't shake them. We can't get rid of them. But if we multiply by a very slightly modified copy of ourselves, where we only do one thing, that's change the sign, this time it went from plus to minus, but if the problem were different where we were given this, all we would have to do is multiply it by its conjugate, which would be 3 plus the square root of 7. You can see you're going to get the same thing, and you're going to eliminate all radicals in the answer. That's going to be the secret of how we killed the denominators that have radicals in there. Second thing is, notice this was quantity plus a quantity squared. We said that does follow this form. We multiplied it the long form, but we could have written it as first term squared plus 2ab plus last term squared. So if we had done that, we would have said, okay, this guy squared plus 2 times this, 2 times this is exactly this term. This squared is this. 2 times this is this. Last term squared is this, all added together. So if you remember the shortcut, you can kind of eliminate all of this and just skip to this line, but you know, I like to show everything. All right, so let's crank along here and move on to the next problem. What if we have 1 plus the square root of 2 times 3 plus the square root of 2. And we're going to multiply this out, but ask yourself, I want you to kind of, in the back of your mind as we go along here, start asking yourself, are we multiplying by a conjugate here? Because I want you to know what a conjugate is, so when we get there, it's not so, so crazy. This is not any kind of conjugate. The conjugate of this term here, the 1 plus the square root of 2, would be 1 minus the square root of 2. The conjugate of this term, 3 plus the square root of 2, would be 3 minus the square root of 2. And neither of those is involved in this guy, so we're just doing a multiplication, nothing special. There's no conjugates involved. So first terms, 3 times 1 is 3. Inside terms, 3 times the square root of 2 gives us 3 times the square root of 2. Outside terms is 1 times the square root of 2. So I'll have 1 times the square root of 2. I'll just write it as square root of 2. And here I have square root of 2 times the square root of 2. So I'll write it as square root of 2 quantity squared. This is multiplied by itself. Now what do we have? We have a whole number of 3. Then we have 3 root 2 and 1 root 2. 3 plus 1 is 4, so what we have is 4 times the square root of 2. And then the cancellation happens here with the square root and the square, so we have another number of 2. And so now we can add the numbers. 3 plus 2 is 5. And then we have the 4 square root of 2, and this is all we can do because the square root of 2 is a prime number in there. We can't simplify it even with a factor tree. We certainly can't add them because we don't have any radicals here. There was no cancellation of any roots. There was no really beautiful simplifications that happened over here because we didn't multiply by any conjugates. But we do have to do regular FOIL, keeping in mind the rules of radicals along the way. All right, so here's our first problem where we have to deal with this conjugate thing again. What if I ask you to simplify the following expression? 1 over 4 minus the square root of 3. 1 over 4 minus the square root of 3. I say simplify that. You look at that and you're like, well, I don't know how to simplify that because there's really nothing on the top. There's only a 1 there. There's nothing to multiply. There's nothing to divide. So what do I do? Well, the only real problem with this expression is you have a radical in the denominator. You don't want radicals in the denominator. Now, it's mostly a historical reason why we don't like that. We don't like that for historical reasons I don't really want to go into. Certainly, 1 divided by 4 minus the square root of 3, it's a number. I mean, you could put it in a computer and get a number out. But historically, when we simplify expressions, we just don't want radicals in the bottom. We want to change it, much like we change fractions, into lowest terms. So, 6/12 is a totally fine fraction. 6/12. 5/10 is a totally fine fraction, no problem. 3/6 is a totally fine fraction, no problem. But in all of those cases, you can just say it's 1/2 because when you simplify all of those, you can get it down to lowest terms. The 3/6 is totally fine, but it's just not simplest. So when we do it, and it's mostly convention, we don't have to simplify fractions, we just do it to get it into the simplest form. And that's what we're doing here. We just don't want radicals in the bottom. We want what we call rationalize the denominator. So I'm going to write that down. We need to what we call rationalize. Rationalize. That's rationalize. You can think of the word rational being well-behaved or some kind of nice, property of something, some well-behaved idea. Well, we're going to rationalize this thing. So this is not sort of well-behaved. We're going to change it, right? So we did rationalize denominators in the past, and the way we did it before was the following. 1 over 4 minus the square root of 3. If the problem were just 1 over the square root of 3 like this, how would we handle it? We've actually done that in the previous lessons. I know that you remember that. And so if it were just 1 over the square root of 3, what we would have done in the past is just multiply by square root of 3 over square root of 3. Because remember, when you multiply these together, you'll get square root of 9. And you know what the square root of 9 is. That's just 3, so you get rid of those radicals. So in the past, when you just had a single radical on the bottom, all you did was multiply by top and bottom, radical over radical, and that worked just fine. So let's try it here and see what happens. Because that's the only radical I have, so let me just try it. Multiply the top, so it'll be the square root of 3 times 1. Multiply the bottoms. I have to multiply these things here. I have to actually do the multiplication. So this gets multiplied by this whole term, which means it goes in and multiplies the 4, and it also goes in here. So 4 times root 3 is just going to be written as 4 times root 3. And then I have a minus sign, so I have to keep that along for the ride. And square root of 3 times the square root of 3 is the square root of well, I can write it a bunch of different ways. Let me write it as a square root of 3 squared, or you can write it as a square root of 9, if not to the cube power, sorry about that, square root of 3 squared. Or you can just think of it as a square root of 3 times 3 is 9. But in any case, what you're going to do in the next step is the point I'm trying to drive at here. You're going to have a square root of 3 on the top. That's okay. Bottom, you'll have 4 root 3 minus 3 because the cancellation here happens. Or you can think of square root of 9 in any case. So what you're going to have is square root of 3 over 4 root 3 minus 3. Notice that I still have a radical in the bottom. So just multiplying by the radical, whatever it is, top and bottom, works perfectly fine if the radical is all you have. But because there's another number here, it screws it all up so that you end up with a radical anyway. So this is no help. I mean, this is totally equivalent to what we started with, sure, but it's just it still has another radical in the bottom, so it doesn't help us. But notice, we said that if we take I haven't proven it to you yet in general, but I said if we take a radical expression when you have a number plus a radical and just multiply by a copy of it but change the signs, then we get rid of all the radicals. So that is the secret of what we're actually going to do here. So let's kind of go here and say, let's go draw a little arrow. This here was an aside. This is not, I mean, it's correct to do it, but it doesn't help us rationalize. What we're going to have is 1 over 4 minus the square root of 3. Now we need to multiply by something that we think will get rid of the radical in the bottom. We have to multiply by the conjugate. The conjugate of the bottom is exactly the same, but we just changed the sign of this. So it'll be 4 plus the square root of 3, and we have to multiply by on the bottom the same thing. You see what we've done is we multiply essentially by 1. This quantity here is 1, so we haven't changed anything, and I can wrap parentheses around here to help me group things. And now when I multiply the tops and I multiply the bottoms, I'll be multiplying the conjugate times, or this thing times its conjugate, which I haven't proven it to you rigorously, but it basically always kills the fractions. Always kills the radicals. On the top, this times 1 is going to give you 4 plus the square root of 3. And on the bottom, we have to actually do the math. We have to do FOIL. So 4 times 4 is 16. Okay. Inside terms, 4 times negative root 3 means negative 4 root 3. Outside terms is positive 4 times root 3 plus 4 times root 3. And then the last, I have a negative, so it's going to be negative. It's going to be the square root of 3 times the square root of 3. So it'll be negative square root of 3, and let's write it as quantity squared, because that's what it is. Now notice what happens here. This negative 4 times the square root of 3 plus a positive 4 times the square root of 3 makes that drop away. And so what I'm going to end up having is 4 plus the square root of 3 on the top. On the bottom, I'll have the 16, and here will be a minus sign. I'm going to cancel the square root with the square. I'll have a 3, so minus 3. And so I will have 4 plus the square root of 3 on the top. On the bottom, what is 16 minus 3? Let me just double check I'm catching up with myself. I'll have 13. And there's really no way to further simplify this. 4 and 13 don't really simplify any better than this. So you have 4 plus the square root of 3 on the top, 13 on the bottom. Notice there are no radicals in the bottom. That's all we were trying to do. This expression here, if you put it in a computer or a calculator, is exactly the same as the one we started with mathematically. It's the same decimal value, but we don't have any radicals in the bottom. Even though this looks maybe even a little more complicated than this one, we consider this one to be the more fully simplified form. It's mostly a convention. It's mostly just kind of like the rules developed over the centuries in math there. Okay, now this is not a theoretical math class, right? But it is true that when you multiply a binomial with a radical like this times its conjugate, which means multiply by a copy, but just change the sign between the terms, we'll always have one of these cancellations like this, which means we will always have no radicals in the answer. And that process is what we call rationalizing the denominator. Right here, rationalizing the denominator. All right, so with that under our belt, let's just cruise along and solve a couple of extra problems to get more practice. What if we have square root of 7 minus square root of 2 quantity squared, right? Now, we can write it as this times itself, but I say, hey, why not every now and then, let's just use one of these rules. We know that this something plus something quantity squared, first term squared plus 2ab plus last term squared. We don't have to do this for every problem, but let's do it for some problems. So what we have here is first term squared, but let's write it as square root of 7 squared so we don't mess anything up, right? But notice this is a minus sign, so this is actually a very slightly different version here. This is first term squared minus 2ab plus last term squared, okay? Minus 2 times the first term, square root of 7, times the last term, square root of 2, right? And then plus the last term squared. Plus, that's what we just said, square root of 2 squared, like this. So let's go ahead and evaluate all this, and we should be able to get to the answer. The cancellation between the radical and the squaring here will leave us with a 7. The minus 2 here will be carried along, but we have radical times radical, so we can bring it under a common radical and make it the square root of 14, because 7 times 2 is 14, so we can bring that inside. And then we have a cancellation there, so we have a plus 2. And then 7 plus 2 is 9, minus 2 square root of 14. So 9 minus 2 square 14, that's the final answer. 14 we can't simplify anymore. If we do a tree, it'll be 2 times 7, so there's no pairs, so we can't really do anything further with it. So this is just an example of using those binomial formulas, you know, first term squared minus 2 times this plus last term squared. But if you were to forget that, which, I forget things all the time, no kidding. I mean, 2 years from now, I probably forget this. It happens to everybody. So let's just go over here. If you forget that rule, that's okay. Just write it as the square root of 7 minus the square root of 2 times itself, which means square root of 7 minus the square root of 2. And you would work it out like this. This term multiply would give you this, minus 2 times the root of 7, minus another 2 times the root of 7. So that's 2 of them. 2 times square root of 7 times square root of 2, because I have one copy here and one copy here with minus signs in front of both. The last term will be positive because of this multiplication, and then the root 2 will be multiplied by itself. So if you forget the rule, that's okay. Just write it down and expand it yourself. All right, let's talk about this conjugate a little bit more. In this case, the conjugate here was a number, not a radical, but just a number, and then a radical here minus the square root of 3. In the first case, we had a number linked to a radical with a sign here. And we said the conjugate means you just take a conjugate, and you take the copy of it and you change the sign. That's all correct. But let's generalize it a little bit more even. Let's say the first thing is not just a number like we've had it in the past. Let's say the first thing here is a full-blown radical. Let's say 1 times the square root of 2 as an example, plus 2 times the square root of 3. So notice this is not just a regular whole number. I have a radical here, there. What would be the conjugate of this? Let's just see what happens. What's the conjugate of this? You just do a copy of itself, but you change the sign of the end. If it's a positive, it changes to negative. But if this were a negative, the conjugate would just change it to a positive. So this is 1 times the square root of 2 minus 2 times the square root of 3. This is taking this and multiplying by its conjugate. So let's go through it and see what happens. If the kind of like the theory holds, we should have no radicals in the answer, right? Because even though I haven't proven it to you, that's what I'm telling you. So the first terms, we're going to do everything very methodically. We're going to write everything out. We're going to say 1 times the square root of 2, 1 times the square root of 2, times this term, which is another 1 times the square root of 2. We're going to write it all out. The inside terms is 2 times the square root of 3 times 1 times the square root of 2. The outside terms means we have a minus sign, and we have a 1 times the square root of 2 times 2 times the square root of 3, but I'm going to write it the same way as this to match it. 2 times the square root of 3 times 1 times the square root of 2. So in other words, this is 2 root 3, 1 root 2. This is also 2 root 3 times 1 root 2. I'm just writing it in the backwards order so it matches exactly. And I have a minus sign from this multiplication, and it's going to be 2 root 3 times 2 root 3. So this is the entire thing multiplied out in all of its glory. Let's see what happens. Okay, let's see what happens. First of all, I'm not going to do all the interior multiplication. You can see that this term exactly matches this one, but it's subtracted. So this whole thing just goes away to 0. The whole thing just disappears because of the way this thing is very slightly unbalanced here. The 1 times 1 gives me a 1. The square root of 2 times the square root of 2 can be written as the square root of inside multiplied together square root of 4. 2 times 2 is 4. The minus sign comes from the end here. 2 times 2 is 4 on the outside. Root 3 times root 3 is going to be the square root of 9, because I can bring them underneath the radical there. And then the square root of 4 is 2 minus 4 times square root of 9 is 3. So what I have is 2 minus 12. 2 minus 12. And what is 2 minus 12? Negative 10. Negative 10 is the final answer. So when you take this larger, more complicated radical binomial here, and you multiply it by its conjugate, an exact copy but just with the sign changed, then you eliminate all radicals and you get just a number. Yeah, you got a negative number in that case, but that's okay. It's just a number. So we're inching ourselves kind of closer to the truth that when you multiply by a conjugate, you kill all the radicals. And to drill that absolutely into the ground a little bit more, we're going to do the most general example here. Let's say we have, take all the numbers out of it completely. Let's say we have a times the square root of b. These can be any numbers. Plus c times the square root of d, right? What's the conjugate of this? It's an exact copy of itself, changing the sign that links them. A times the square root of b minus c times the square root of d. And it doesn't at this point matter what a and b and c or d are, but because we have the variables labeled and they're exactly the same places here, it's the same copy of itself with just a minus sign here. So we're going to do our best to kind of like prove that this works for everything. So when we have this times this, we're going to write it all out. We're going to say that's going to be a times the square root of b times a times the square root of b, multiplying these. The inside terms are going to be all these multiplied together, and I'm going to write that as c times the square root of d times a root b, just this times this term. But then I have a minus sign when I multiply these, so that minus sign goes there, and it's c root d times this one. So I'm going to write it as c root d times a root b. And so what I have in the last position is these multiplied together. So I have a negative times a positive, which gives me negative c times root d, c times root d. So c root d times c root d, minus sign there. Now, before I go any farther, I see right away that this entire center term just cancels and goes to 0 because even though it's giant, c root d times a root b, c root d times a root b. There's a subtraction, so they all go away. And then finally, what I'm going to have here is a times a giving me a squared. Square root of b times square root of 3b is square root of b squared because I can multiply the b's under the radical. I have a minus sign from here. C times c is c squared. And then square root of d times the square root of d, which means square root of d squared there. And then I can see I'm going to have a squared times this cancellation here will be b minus c squared, this cancellation d. So I have a squared b minus c squared d. So the point is that when I take anything, even a radical with numbers and all this under the radical and outside the radical linked with some similar term, multiplied by an exact copy of itself, only changing the sign, I again get something back that only has numbers but no radicals involved. That's really the only reason I'm telling you that. So in order to rationalize the denominator of any large fraction like that, we're going to multiply the top and the bottom by what we call the conjugate. And you should get used to the idea of conjugates, to be honest with you, because we're using conjugates in lots of problems to rationalize denominators, but pretty soon we're going to get to the idea of imaginary numbers and complex numbers, which we're going to talk about later, and we actually have complex conjugates. So conjugates that are related to complex numbers, we have to deal with that later as well. So the idea of a conjugate is not going to go away, but it's just a special way of multiplying by a very similar term that gets rid of the radicals. That's all we're kind of worried about here. So make sure you can do this. We did a lot of problems here, some with rationalizing, some that didn't need to be rationalized. I want you to solve all of these. Follow me on to the next lesson. We have several more lessons to give you more and more practice with multiplying binomials that contain radicals.